In the spring of 1962, a bank in Ohio was facing a problem that had nothing to do with money and everything to do with machines. The bank had grown. Its old computer, a machine that had been state-of-the-art 5 years earlier, could no longer keep pace with the volume of checks, deposits, and account records that the bank's expansion had produced. The solution seemed obvious: buy a newer, more powerful computer from the same manufacturer that had sold them the first one. The obvious solution turned out to be almost useless. The newer, more powerful machine did not run the bank's existing programs. It used a different instruction set, a different way of representing numbers, different tape drives, different everything. The thousands of hours that the bank's programmers had spent writing and refining software for the old machine were not transferable. They were not even partially transferable. They were simply gone, the way a library of books written in one alphabet is gone to a reader who only knows another. To upgrade, the bank did not add a computer. It replaced one civilization with another. New programs had to be written from scratch. New staff had to be trained from scratch. The institutional knowledge built up over years of operating the old machine had to be rebuilt, at enormous cost, in a new and incompatible language. This was not a story about one unlucky bank. This was the condition of computing itself in 1962. Nobody in the computer industry in 1962 described this as a crisis, because the condition was so universal that it did not feel like a problem requiring a solution. It felt like weather. Computers got better. When they got better, you started over. This was simply understood to be the price of progress, the way a homeowner in an earlier century might have accepted that a house occasionally burned down and had to be rebuilt, unfortunate, expensive, but not something anyone seriously proposed eliminating. International Business Machines, IBM, was in 1962 the dominant company in this fractured landscape, and its dominance was itself a symptom of the fracture. IBM did not sell one computer. It sold 7 largely incompatible families of computers: the 1401 for small businesses, the 7070 and 7080 for larger commercial accounts, the 7090 and 7094 for scientific and engineering customers, the 1410 for a different tier of business customer, and others besides. Each family had its own engineering team. Each family had its own operating software, written by different groups who rarely spoke to one another. Each family had its own set of peripheral devices, tape drives, printers, card readers, that worked with that family and with nothing else. A customer who outgrew the 1401 and needed the power of a 7080 was not upgrading. They were emigrating. Everything they had built had to be left behind at the border. This arrangement was not the product of incompetence. It was the product of a computer industry that had grown by accretion, one product line stacked on another, each one designed to solve an immediate engineering problem without much thought for what would come after it. IBM had become the largest computer company in the world by being good at building individual machines. It had not yet had to be good at building a coherent strategy across machines, because no one else had managed that trick either. But the world that IBM was selling into was changing in a way that made the old arrangement increasingly untenable. The early 1960s in the United States were a period of explosive, almost reckless expansion in the use of computers by ordinary businesses. The computer was migrating out of the research laboratory and the military installation, where it had spent its first 15 years of existence, and into the back offices of insurance companies, airlines, retailers, and banks, institutions that had no interest in the elegance of a machine's architecture and every interest in whether it could process payroll on time. This migration created a demand for computing power that was doubling, by some industry estimates, every 2 or 3 years. It also created a new and uncomfortable problem for IBM's customers, and for IBM itself. Every time a business grew large enough to need more computing power than its current machine could provide, it faced the prospect of the Ohio bank's predicament. A wholesale changeover, a new machine, a new language, a new staff of programmers, a new and expensive beginning. IBM's competitors, a group of companies that the industry, with a certain amount of unkindness, had begun calling the 7 dwarfs in deference to IBM's status as Snow White, were watching this problem closely because it represented an opportunity. Honeywell, General Electric, RCA, Control Data, Sperry Rand's UNIVAC division, Burroughs, and NCR could not match IBM's size or its sales force, but several of them were experimenting with something IBM had not yet offered. Machines designed from the outset to share software within a single family, so that a customer who outgrew one model could move to the next without starting over. If this idea caught on broadly, IBM's dominance, built on the strength of its biggest machines and its most prestigious scientific customers, was vulnerable to being undercut from below, model by model, customer by customer, by competitors offering something IBM's fragmented product line could not. The man who had to decide what to do about this was not an engineer. He was the company's president, and he had spent much of his career trying to prove that he deserved the job. Thomas J. Watson, Jr., had become president of IBM in 1952 and its chief executive in 1956, the same year his father, Thomas Watson, Sr., the formidable patriarch who had built IBM from a maker of scales and tabulating machines into a corporate institution, died. The younger Watson was, by his own later account, and by the account of nearly everyone who worked with him, a man who lived for years under the suspicion that he had inherited a company he had not built and might not be capable of running. He was in his late 40s in the early 1960s, a decorated former Army Air Forces pilot, restless, impatient with caution, and acutely aware that IBM's reputation for reliability, a reputation his father had spent 4 decades constructing, could become a liability if it calcified into an unwillingness to take risks. Watson, Jr., wanted IBM to be known not just as a company that built dependable machines, but as a company that defined what computing was. He did not want to inherit his father's company, he wanted to remake it. In 1961, Watson commissioned a task force inside IBM to study the company's product line and recommend a direction for the future. The task force became known, from an acronym for its mandate, as Spread Systems Programming, Research, Engineering, and Development. It was led by a senior engineering executive named Bob Evans, and it included some of the most capable and most argumentative engineers in the company. The Spread Committee's conclusion, delivered to Watson in late 1961, was not a recommendation for a better computer. It was a recommendation to abolish the entire existing product line and replace it with something that had never been built before, a single family of computers, spanning from small machines for modest businesses to enormous machines for the most demanding scientific customers, all of which would run the same software. This was not an incremental improvement. This was a proposal to set fire to 7 existing, profitable product lines, representing the majority of IBM's revenue, and bet the company's future on a single, unproven architecture that did not yet exist in any working form. The conventional wisdom inside the computer industry in 1961 held that this was, if not impossible, at least unwise. Scientific computing and business computing had different needs. Scientific applications demanded fast arithmetic on large numbers. Business applications demanded efficient handling of large volumes of relatively simple data, payroll records, inventory counts, account balances. The machines that served these markets had evolved different internal designs because the markets had different requirements. Building one architecture that served both well and that could be physically realized in models ranging from a small office machine to a room-sized scientific computer was assumed by most engineers in the industry to involve compromises severe enough to make the resulting machines mediocre at everything. The engineer who became most responsible for proving this assumption wrong was a large, blunt, combative man from a farm in South Dakota named Gene Amdahl. Amdahl had joined IBM in 1952 after completing a doctorate in physics, and he had already been through one significant professional disappointment by the time the Spread Committee did its work. A project called Stretch, an enormously ambitious scientific supercomputer that IBM had built for Los Alamos National Laboratory earlier in the decade. Stretch had been a technical marvel in some respects, but it had not hit its performance targets, and the disappointment had strung Amdahl personally since he had been one of its chief architects. What Amdahl took from the Stretch experience was not caution. It was a conviction that the next big architectural bet had to be right in a way that Stretch had not quite managed, and that the bet should be ambitious enough to matter. When the spread committee's radical proposal for a unified, compatible computer family reached the design stage, Amdahl became its chief architect, the engineer most responsible for turning the idea into a buildable machine. The idea itself required solving a problem that sounded almost philosophical. How do you design a single instruction set, a single underlying language that the machine understands, that can be physically implemented in a small, slow, inexpensive computer, and also in a large, fast, expensive one, such that a program written for the small machine will run, without modification, on the large one? The answer that Amdahl's team developed depended on a layer of the machine's design called microcode, a thin layer of instructions built into the hardware itself that translated the family's common instruction set into whatever specific electronic operations a given model's actual circuitry could perform. The small machine and the large machine could have entirely different internal electronics, different speeds, different costs, and the microcode layer would make both of them present the same face to any program that ran on them. A customer's software did not need to know, and would never need to know, what was happening underneath. This was an elegant solution to an enormous problem. It was also a solution that nobody had implemented at this scale before, in a family of machines this large and this commercially important, and elegance on a blueprint is not the same thing as a working machine on a factory floor. The architecture needed one more decision that seems trivial in retrospect, and was anything but trivial at the time: how the machine would represent a single unit of data internally. Existing IBM machines used a confusing variety of word lengths and data representations, inherited from a decade of separate engineering teams making separate decisions. The new family needed one standard, used consistently across every model, every peripheral, and every piece of software. The team settled on an 8-bit unit, which they called a byte, a term that had existed in computing jargon for a few years, but had never been standardized as the fundamental currency of an entire major computer architecture. The decision to standardize on the 8-bit byte, made inside a conference room as part of solving an internal compatibility problem, would turn out to be one of the most consequential and least celebrated decisions in the history of computing. Nearly every computer built in the world today, including the device most people are using to watch a video about this story, still organizes its memory in 8-bit bytes, a direct descendant of a choice made to solve a 1961 engineering headache that had nothing to do with the future and everything to do with making one bank's accounting software run on the same machine as one physicist's missile trajectory calculations. The hardware, difficult as it was, turned out to be the smaller of the project's two crises. A family of compatible computers needs more than compatible hardware. It needs an operating system, the software that manages the machine's resources, runs programs, handles input and output, and presents a consistent environment to every application that runs on top of it. And that operating system needs to work with the same essential behavior across machines that might differ in raw computing power by a factor of 50. No operating system of this scope and ambition had ever been attempted. IBM assigned the task to a software division that grew, over the course of the project, to include more than 1,000 programmers, working under a manager in his early 30s named Fred Brooks. Brooks was a North Carolinian, trained at Harvard, under one of the field's pioneering computer scientists, and he had the kind of clear-eyed intelligence that allowed him, even while the disaster was happening to him personally, to understand exactly what kind of disaster it was. The software project, which IBM called OS 360, ballooned in scope as the hardware family's ambitions expanded. Estimates of how long it would take to write proved wrong by margins that embarrassed everyone involved. When the project fell behind schedule, the instinctive management response was to add more programmers, on the assumption that a task behind schedule could be brought back on schedule with more hands. This instinct was catastrophically wrong, and the OS 360 project became the data point that proved it wrong on a scale impossible to ignore. Adding programmers to a late software project did not speed it up. It slowed it down further, because every new programmer had to be brought up to speed by existing programmers, consuming the time of the very people whose work was already behind, and because the communication overhead among a growing team grew far faster than the team's growing size could be expected to compensate for. Brooks would later distill this observation into a principle that has been quoted by software engineers ever since, that adding manpower to a late software project makes it later. By 1964, the OS 360 effort had consumed far more money and far more time than anyone at IBM had projected when the spread committee made its initial recommendation. The hardware, while also behind schedule, was at least a tangible thing that could be inspected on a factory floor. The software was an enormous, sprawling, only partially functional set of promises, owned by a team that had grown so large it had begun to generate the very delays it was meant to solve. By the time IBM was ready to announce what it had built, the company had committed an amount of money to the project that dwarfed anything in its previous history, and that compared, in adjusted terms, to the cost of building the atomic bomb. Estimates of the total cost of developing the new computer family and its software, including new factories built specifically to manufacture it, ran past $5 billion, a figure that made the project, by a wide margin, the largest private commercial investment that had ever been undertaken by a single American company up to that point in history. IBM's total revenue at the time was a fraction of that figure. The company was not spending money on a new product line. It was spending money on a bet that, if it failed, could plausibly bankrupt IBM or force a sale of the company to someone else. Thomas Watson, Jr., understood the stakes with a clarity that several of his colleagues later described as close to terror. He had inherited a company built on his father's reputation for never promising a customer something IBM could not deliver. He was now committing that company's entire future to a machine that, as the announcement date approached, did not yet fully work, ran on an operating system that did not yet fully function, and depended on an architectural bet universal compatibility across a vast range of machine sizes that no one in the industry had proven was even achievable. Watson would describe the decision, in later years, as the most important and the most frightening that he made in his career at IBM. Inside the company, engineers and executives who lived through the project's worst months in 1963 and early 1964 used a phrase, only half in jest, to describe what they were doing, betting the company. IBM announced the System 360 on April 7, 1964, in a series of coordinated events held simultaneously in 63 American cities and 14 countries. A scale of product announcement that no computer company and few companies of any kind had previously attempted. In New York, IBM rented the Coliseum and the Waldorf Astoria and filled them with reporters, customers, and IBM salesmen who had themselves only learned the full scope of what they were selling days earlier. Thomas Watson, Jr., stood in front of the assembled press and described the announcement, without exaggeration, as the most important product event in the company's history. The company unveiled not one new computer, but a family of 6 models, ranging from a modest machine intended for smaller businesses to a powerful flagship intended for the most demanding scientific and engineering customers, all of them sharing the same architecture, the same instruction set, and in principle, the same software. Orders flooded in at a pace that startled even the executives who had pushed hardest for the project. Customers understood immediately what the System 360 offered that no previous computer family had, a way to grow without starting over. A small business could buy the smallest model and know that, years later, when it outgrew that machine, the larger model down the line would run the same programs without modification. The fundamental and unglamorous problem that had plagued the Ohio Bank and thousands of customers like it, the terror of the incompatible upgrade, appeared, on paper, to be solved. What the announcement did not fully reveal, and what became apparent to customers over the following 18 months, was that the System 360 in April 1964 was a promise more than it was a finished product. The hardware for the larger models was not ready to ship on the timeline IBM had announced. Some models slipped by months. The operating software, OS 360, The project that had consumed Fred Brooks's team and grown far beyond its original schedule was, through much of 1965 and into 1966, incomplete, unreliable, and in places simply absent. Customers who had ordered machines on the strength of IBM's announced capabilities received computers that ran early, stripped-down versions of the promised software, with features arriving in installments, sometimes a year or more late, sometimes accompanied by bugs serious enough to halt a customer's operations. Trade publications covering the computer industry in 1965 reported customer frustration candidly. IBM's own internal assessments, made public decades later in corporate retrospectives, acknowledged that the company had announced a product before it was ready to deliver it, under competitive pressure, and under the pressure of an enormous and growing investment that the company needed to start generating revenue against. By any reasonable standard applied honestly in 1965, the System 360 program was behind schedule, over budget, and shipping a product that did not yet do everything its own advertising claimed. A skeptical observer, looking at IBM's balance sheet and its unmet software deadlines in the middle of 1965, could have reasonably concluded that Thomas Watson Jr. had bet his father's company and was losing. The System 360 did not fail. Over the following 2 years, IBM's software teams, chastened, restructured, and operating under the hard lessons that Fred Brooks would later turn into one of the most influential books ever written about software management, brought OS 360 to a level of functionality and reliability that satisfied the bulk of IBM's customer base. The hardware, manufactured in new factories built specifically for the project, reached volumes that no computer family had previously approached. By the late 1960s, IBM was producing System 360 machines at a rate measured in the thousands per year, across a customer base that included banks, airlines, government agencies, universities, and manufacturers around the world. The compatibility promise, imperfect as its early execution had been, turned out to be exactly the feature that the market wanted and that no competitor could easily match. A customer who bought into the System 360 family in 1965 could upgrade in 1968 and again in 1971 without the wholesale rewrite that had defined computing in the world before 1964. The seven dwarfs, who had hoped to pick off pieces of IBM's customer base, found that IBM had instead built a structure that made staying with IBM more attractive than it had ever been. By the early 1970s, the System 360 and its direct successors had made IBM not merely the largest computer company in the world, but a company whose architecture had become, in practical terms, the standard that the rest of the industry had to define itself in relation to. The 8-bit byte that Amdahl's team had standardized to solve an internal engineering problem became the unit that essentially every subsequent computer architecture, including the personal computers and smartphones built decades later by entirely different companies for entirely different purposes, would also adopt. The financial bet that had threatened, in 1963 and 1964, to be the most expensive mistake in the history of American business, turned out instead to be the foundation of IBM's dominance of corporate computing for the next quarter century, and the direct ancestor of the mainframe computers that even now run the back-end systems of a large share of the world's banks, airlines, and governments. Machines whose lineage traces directly back to the architecture Gene Amdahl's team designed under the threat of corporate bankruptcy. The irony embedded in this story is one that the people who lived through it were, in some cases, uniquely positioned to recognize, because the crisis itself produced one of the most important and lasting contributions the project made to the wider world, a contribution that had nothing to do with hardware at all. Fred Brooks left IBM in 1965 to found the computer science department at the University of North Carolina, and in 1975 he published a book about his experience managing the OS 360 project, called The Mythical Man Month. The book's central observations, that large software projects fail in predictable ways, that adding people to a late project makes it later, that complex software systems need a small number of people holding a coherent vision rather than a large number of people working in parallel without one, were drawn directly from the specific catastrophe of building OS 360. These observations, born from a project that nearly bankrupted IBM, and that was, by any fair accounting, badly mismanaged in its early stages, became foundational reading for generations of software engineers and managers who followed. Decades after the System 360 itself had become a historical curiosity, the lessons extracted from its worst months were still being taught to people building software for companies that did not exist when OS 360 shipped, companies building the Internet's infrastructure, the operating systems inside personal computers, the software running inside phones. The machine that should have failed did not simply succeed despite its near-disastrous development. Its near-disastrous development became one of the most valuable things it produced. Gene Amdahl, the architect who had carried the System 360's central technical bet on his own reputation, did not stay at IBM long enough to enjoy the full scale of what he had built. He remained with the company through the early 1970s, rising to the rank of IBM Fellow, one of the company's highest honors for a technical contributor, and continuing to push for ever more ambitious successors to the architecture he had designed. IBM's management, increasingly cautious after the financial trauma of the original System 360 program, repeatedly declined to fund the scale of expansion that Amdahl believed the next generation of mainframes required. The same instinct for risk that had served Amdahl well in 1961, when caution might have killed the entire project before it began, made him an uncomfortable fit inside a company that had nearly bankrupted itself once already and had no appetite for doing so again. In 1970, Amdahl left IBM and founded a company that bore his own name, with the explicit purpose of building mainframe computers compatible with IBM's System 360 architecture, faster in some cases, priced more aggressively than IBM's own machines, but built to run the exact same software, because the software and the customers who depended on it were where the value had always actually resided. Amdahl Corporation became, for more than a decade, one of IBM's most serious competitors in the mainframe market, competing directly against the descendants of the very machine its founder had designed. This is a second and quieter irony layered on top of the first. The compatibility that Amdahl had built to keep IBM's customers from ever needing to abandon their software for a competitor's machine turned out, in his own hands, to be the exact mechanism by which a competitor could enter IBM's market without asking those customers to abandon anything at all. The architect of IBM's greatest gamble became, a few years later, the most credible threat to the empire that Gamble had built. It is difficult, looking at a computer from this distance, to feel the scale of what was actually being decided when Thomas Watson Jr. approved the System 360 program. The machines themselves, by today's standards, were almost laughably modest, refrigerator-sized cabinets containing processing power that a wristwatch would later exceed by orders of magnitude. The drama was not in the silicon. The drama was in the bet. That compatibility, the unglamorous and unsexy idea that a computer should not betray its customers' accumulated investment every time it was outgrown, was worth gambling an entire company's future on. That bet, made by an anxious son trying to prove himself worthy of his father's company, executed by a combative farm-raised physicist who had already failed once on stretch, and nearly derailed by a software crisis that consumed 1,000 programmers and birthed an entirely new discipline of software management, turned out to be correct. It turned out to be more than correct. It turned out to define what a computer was, structurally, for everyone who built one afterward. The bank in Ohio that began this story did not know, in 1962, that an answer to its problem was already being designed in a conference room inside IBM, by engineers who themselves were not yet certain it would work. 2 years later, that answer arrived, late, expensive, and incomplete in its first form, and went on to become the invisible foundation underneath nearly every digital transaction that the modern world now takes for granted. The System 360 sits today in the form of a few preserved consoles and processing units, in museums of computing history, including the Smithsonian's collections, large, beige, unglamorous machines with banks of blinking lights that look, to modern eyes, almost comically primitive. They do not look like the beginning of the digital world. They look like furniture from an office that closed decades ago, the kind of machine a visitor might walk past without a second glance on the way to an exhibit about something more visibly dramatic. A rocket, a satellite, a famous first home computer with a recognizable name still printed on products today. That too is exactly the point. The most consequential bet in the history of corporate computing did not announce itself with a sound or a spectacle that a museum could easily stage. It announced itself with an 8-bit unit of data, a layer of hidden microcode, and a promise, kept imperfectly at first, and then kept completely, that a customer who grew would not have to start over. Everything that came after, every compatible upgrade across every generation of personal computer and corporate server, every byte of data moved across every network built in the 6 decades since, rests on a gamble made by a worried son trying to prove himself, an architect still smarting from one failure already, and a young manager who would turn his own project's worst year into the most widely read book ever written about why software projects go wrong, a gamble that, for most of 2 harrowing years, looked very much like it was not going to pay off at all.